In the previous lecture, I had given an example of a vector as v equal to 100 km per hour south. In doing so, I had skipped an important step in the quantification of a vector. The missing step was the description and definition of reference directions to which vectors in the problem will be compared to. The choice of these reference directions will be dictated by the need for simplification. When I stated in the example that the direction was towards the south, I had assumed that the meaning of a southward direction had been explained previously in some geography course. In that example, the reference direction was also the direction of the vector. In general, it will not be the case. In general, if one is working with a situation where the vectors have no restriction in their directions, then it is necessary to define three reference directions. This is called a three-dimensional case. The notation and the method used to describe the reference directions is to explain them in relation to the physical or geographical setup in the problem. Three unit vectors, labeled x hat, y hat, and z hat, and parallel to the reference directions, are created. These three unit vectors must be perpendicular to each other. Three unit vectors that would satisfy these conditions are the following. X hat and y hat are both horizontal direction, so they are perpendicular to z hat, which is vertical. And the eastward direction is perpendicular to the northward direction. In this course, we will not be working with three-dimensional cases. However, we will be working with situations where all vectors are parallel to a plane, in which case only x hat and y hat need to be defined, provided that they are both parallel to the plane. We will also work with even simpler situation, where all vectors are parallel to a straight line, in which case only defining a x hat parallel to that line will be enough. Let us say that you want to describe vector A in relation to the following set of reference directions, where x hat points towards the right and y hat points towards the top of the page. You can always draw two vectors parallel to the reference direction, and that once added will be equal to the vector A. Vector A1 is parallel to x hat, and vector A2 is parallel to y hat. There exists a real number which multiplied by x hat can be made equal to the vector A1. We will label it AX. Similarly, a real number can be found that once multiplied by vector y hat will create the vector A2. We will label it AY. Once you know AX and AY, you have a new way of describing a vector. The vector is said to be written in component form. AX is called the x component of vector A, while AY is called the y component of vector A. Notice that these components have the same measurement units as the vector itself, and because we have drawn a right-angled triangle, we can use the Pythagorean theorem to write a relationship between the magnitude of the vector and its components. Before we go over an example of converting a specific vector into component form, I would like to summarize the elements that need to appear in the numerical solution to a physics problem. First, make a drawing. Example of what is useful to draw are your choice of reference directions, the labeling of various quantities, and the drawing of arrows as visual representation of vectorial quantities. The second element is the association of variable names to the numerical quantities in the problem. In the lectures, a particular letter will be assigned to each physical quantity. This association can be shown in a list of givens, or it can be done when substituting the numerical values once a theoretical mathematical equation has been presented. The third element is about the stating of those mathematical relationships. They should not use any numerical values at first, only variable names. Otherwise, your solution looks like a bunch of numbers added, multiplied, or divided without any sort of justification. Finally, the last element is the final numerical answer, written with its measurement units as well as with the proper number of significant digits, if only simple operations between independent quantities have been used. In this example, the reference directions have already been chosen. If you use a different set of reference unit vectors, it would lead to different values for the components of any vectors. I have given 3 different ways of presenting the direction of the same horizontal vector A. The first way requires more words, and the last 2 ways are typical abbreviated versions. East 36.9 degrees south means that the vector A points roughly towards the east, but it is deviated towards the south side of east by 36.9 degrees. The third way deviates a southward vector by 53.1 degrees towards the east side of south. The complementary angle to 36.9 degrees was used here. The first element of the solution is to make a drawing. When using east and north unit vectors, it is customary to point the eastward direction towards the right of the page and the northward direction towards the top of the page, as you would do on a map. The vector we are dealing with would then look like that. Since we are interested in its components, we will show this vector as a sum of 2 vectors parallel to the reference directions. We will choose the letter theta for the angle of deviation of vector A compared to the eastward direction. Since trigonometric ratio will be used to calculate the components, we will label the sides of the triangle with positive variable names proportional to each side length. The hypotenuse is proportional to A. The side parallel to x hat is proportional to the absolute value of the x component, and the last side is proportional to the absolute value of the y component. Our list of givens looks like this. To calculate the x component, we will use the definition of the cosine of angle theta, which is the ratio of the length of the adjacent side and the hypotenuse. Using the labeling of our triangle, it is also the ratio of the absolute value of the x component and the magnitude of the vector A. Rewriting this equation to isolate for the absolute value of the x component gives this. To decide about whether AX is positive or negative, you need to compare the direction of the blue vector to the direction of x hat. They are both eastward, so the scalar needed to create the blue vector will have to be positive, which means that AX equals the absolute value of AX. Using that last piece of information, we can write AX equals to A times cos theta. Substituting the numerical values leads to a value of 4 meters per second for the x component of vector A. We didn't go over rules about the propagation of error when trigonometric functions are involved. However, it is probably a safe bet to use the same number of significant digits as the input number with the lowest number of significant digits. In a similar way, we will now evaluate the y component of vector A. This time, sine theta will be used because it involves the y component. Using the labeling of the triangle, we get that sine theta equals the ratio of the absolute value of the y component and the magnitude of vector A. Rewriting this equation gives this. Comparing the southward green vector to the northward y hat, we find that in order to create the green vector by multiplying the y component with y hat, we need the y component to be negative. it leads to this. Combining the last two equations gives the final mathematical equation for the y component. Substituting the numerical values for the angle and the magnitude of vector A leads to the y component to be equal to minus 3 meters per second. All that is left is to write the final answer in component form. My final example is about converting a vector given in component form to the same vector expressed in terms of magnitude and direction. The same set of reference directions as in the previous example is used here. Vector B is the result of the addition of a vector with a negative x component, so pointing westward, a direction opposite to the one of x hat, and a vector with a positive y component, so pointing northward in the same direction as y hat. The vector B looks like this. I will define theta this way. It means that vector B will be described as pointing roughly to the west and deviated to the north side of west by an angle theta. As before, I will label the side lengths of this right-angled triangle with positive variable names proportional to the side lengths. The list of givens is the following. Since what is given are the opposite and adjacent sides, we will use tangent theta to evaluate theta. Isolating for theta gives this, and substituting the numerical values for the components gives an angle of 60 degrees. Now onto the task of evaluating the magnitude of vector B. The Pythagorean theorem is used to give an expression for the hypotenuse, which here is proportional to the magnitude of vector B. Substituting the numerical values for the components gives a magnitude of 1 meter. All that is left is to combine all this information to write the final answer. Now armed with a working knowledge of vectors, we can move on to the task of quantifying physical phenomena. The first topic is kinematic, which is the study of motion. We will start with trying to answer the question, where is an object? This will be the subject of the next installment.